Hey everybody, Dr. Retzek here with you. This is our first video in our final section of Math 406. This is section 7D on polar decomposition. Let's get started. The purpose of today's video is to point out an analogy between the set of complex numbers and the set of linear operators on a finite dimensional inner product space. So we have two pictures. The first picture is just a picture of the complex plane. So this is C. Now, in the complex plane, you have complex numbers. So this number here, Z equals A plus BI. And you have this action called conjugation, where to conjugate is simply to reflect across the real axis. So you have this number, Z bar, which is A take away BI. Now sometimes when you conjugate a complex number, it stays the same. But you can see that only happens when B is 0. So the set of complex numbers whose conjugates are themselves is simply the set of real numbers, here in blue. Now, among those numbers, among the reals, some of them are bigger than or equal to 0. And that's these numbers. Here in red, the non-negative real numbers, which we could denote with R plus. Okay, let's start building this analogy. So there's the complex numbers. Meanwhile, there's this big box consisting of all possible linear operators on an inner product space V. So a typical member of this box is an operator T. And there's this action in this box called taking the adjoint. So this operator T has what's called an adjoint. T star. Now, sometimes when you take an adjoint, nothing happens. These are the so-called self-adjoint operators. Say these. So that blue box, that's the self-adjoint. Operators. Okay, within that blue box, some self-adjoint operators are positive. So a subset of that blue box is this red box. So those are the positive operators. Okay, and you guys actually, you know examples of operators that live in that red box. Well, there's this operator, it's kind of silly. The zero operator lives in the red box, and the identity operator lives in the red box. There's a few things that live in the red box. Okay. Now, returning to the complex plane, certain members of the complex plane are special, in that they are 1 unit from the origin. So that circle there in green is the unit circle. So some numbers are on here, and the way to tell if a number is on there is if z conjugate times z is 1. Because z conjugate times z, I mean, just multiply it out. That's a minus bi times a plus bi. So that is a squared plus b squared, which is the square of the distance to the origin. Okay. Now, if you're seeing the analogy in these two pictures, then what you're seeing is down here, we have take the adjoint. And up here, we have take the conjugate. So somehow, in the realm of complex numbers, taking the conjugate is an analog in the realm of operators on inner product spaces to take the adjoint. The real numbers in the complex plane are those whose conjugates equal themselves, and those correspond to the self-adjoint operators. Down there, among the linear operators on V, those are the ones where the adjoint equals the original operator. Now, within the real numbers, some of them are positive. Non-negative, I should say, 0 included. Within the self-adjoint operators, some of them are positive. Examples of positive real numbers are 1 and 0, where positive really means non-negative. Examples of positive operators are the identity and 0. So now we have to think about, all right, fine, well then what's the analog to the unit circle in the complex plane down here? Well, keep your analogy strong. If the unit circle up here is the complex numbers with the property that z bar z equals 1, then down here it should be operators with the property that s star s equals I. But you know from 7c What operators satisfy S star S equals I? These are precisely the isometries. So the collection of operators down here, corresponding to the unit circle in the complex plane, is the isometries. These. So I is an isometry. 0 is not an isometry. Some isometries are self-adjoint. Others are not. All isometries are normal because S star S and SS star come out the same. Some isometries are even positive, like the identity. So that collection there is the isometries. Okay. Those two pictures are gold for keeping track of who lives where. So positive operators are nested way down in there. They're self-adjoint. The isometries visit the positive operators and they visit the self-adjoint operators, but other isometries aren't. Like think about, I don't know, rotation by 90 is definitely not an isometry. Is an isometry is definitely not self-adjoint. What am I saying? Rotation by 90 is an isometry and is not self-adjoint. So would live out here somewhere. In R2, rotation by 90 would be an example of an isometry that is not self-adjoint. Okay, so we have these pictures is the point, and we have all sorts of different operators we've been interested in. Now there's one last property of numbers in the complex plane that might point to an analogous property for linear operators. Let's get a clean picture of the complex plane. There's C. Here is the unit circle. And here is some number, Z. So that Z is definitely not on the unit circle. So maybe it's 3 units. Excuse me, maybe it's 3 units from the origin. But it has a cousin that is on the unit circle, and that cousin is Z divided by its own magnitude. Okay, so in that picture you can see, oh, okay, great. So any complex number, Z, is equal to its cousin on the unit circle times its own magnitude. I mean, that's clear just by algebra. Absolute value Z cancels, top and bottom. So that's a true statement. Now, where is this number? Absolute Z. is there. That is the positive number representing the distance from z to the origin. And that is the square root of z bar z. So for any complex number z, you can write it as z over absolute z times square root of z bar z. This piece of that description is on unit circle. This piece is a positive square root. Okay. Can we turn this into something operator theoretic? Remember your analogy. In C, taking the conjugate is analogous in L of V to taking the adjoint. We just argued that literally any number in C, like this one, can be written as something on the unit circle times a positive square root of z bar z. This makes us guess that any t in LV can be written t equals, okay, who's going to play the analogy to this piece here? That piece is on the unit circle. The unit circle is analogous to the isometries. So you can write t as an isometry times, now, what's going to be analogous to this piece? Well, z bar is analogous to t star. So this piece here is a positive square root of t star t, and this part here is an isometry. And we are guessing that any operator can be written as an isometry times positive square root of t star t. Now, let's make sure we believe in this positive square root of t star t. Consider the operator t star t. T star t, this operator here, is positive. That's easy to check just by definition of positive operator. And so you know it has a unique positive square root, and that's what this symbol here represents, the unique positive square root. of the positive operator T star T. So if this is true, this will be a great step forward for us because it'll show us that any operator, no matter how crazy, not normal, not isometry, not self-adjoint, not positive, just some random operator T, at the very least, can be decomposed into an isometry times the positive square root of T star T. And that's called the polar decomposition theorem. And it comes from this statement here, which is the polar decomposition of a complex number in the complex plane. So that's where the name polar decomposition comes from. All right, we're going to put all of our skills from really the whole course and especially from 7C into use to prove this polar decomposition theorem next time. Remember your analogy. This picture speaks 1,000 words. That's how to keep track of all the different things that we've studied here in Chapter 7. Okay, see you next time.